Hey guys, Tashrives here, and today I'll be explaining why when you take into account air resistance and you throw up a ball and you let it come down, why the path upwards takes a shorter time than the time that comes down. So as we know, in a case where there's no air resistance, then the time taken to go up is the same time as the time taken to come down. However, when there is air resistance, the time taken to go up is shorter than the time taken to come down, and in this video I'll show you in a more rigorous way why. So let's jump over to quick the quick explanation that is often given. So often people say that when the ball is on the way up, the gravity and air drag acts to slow it down, and when the ball is coming down, then the air drag acts in the opposite direction as gravity, and that also leads to a phenomenon of like terminal velocity. But I feel that that's not fully rigorous, because the starting velocity they start throwing it up at, and then it reaches zero, the starting velocity is going to be different from the velocity when it reaches the floor. So in this video I will try to show you a more rigorous explanation using the concept of distance. So instead of expressing velocity as a function of time, in this video I seek to explain velocity as a function of distance, and let's see how far we can go with the explanation. So let v1 and v2 be the speed of the ball as a function of height x. So we know that the ball goes up and goes down, so let the maximum height be h, let's say, and we know that in both scenarios, when it reaches the peak, it reaches a height h, right? Then it comes down, it starts from a height h also, and then when it reaches the ground, it's a height of 0. So it goes from 0 to h, and it falls back down from h to 0. So let v1 be the speed of the ball on the way up, and v2 be the speed of the ball on the way down. So we say speed over here because we know that on the way up, clearly the velocity is pointing in the upward direction, so there's almost no ambiguity, and we know that when on the way down, the velocity is always pointing in the down direction, so once again there's always no ambiguity. So let's see a scenario where it goes up. So when it goes up, let's say the path, right, I divide it into many steps. So it goes from x equals to 0, height 0, to 0.1h, to 0.2h, to 0.3h, and so on all the way to h. So we know that let's try to get a feel of the function v1 as we traverse from height 0 to height h. So we know that because gravity and air resistance is a force, and it acts downwards on the ball on the way up, then v1 is a decreasing function of height, meaning that the higher you go, the slower the ball is, which completely makes sense, right? Okay, then we also know that v2 is a decreasing function as a height, because we know that when the v2 starts from the top of the journey, when it starts at height h is equals to 0, as it comes down, it speeds up faster and faster. So if we plot the speed as a function of height, then we know that at the bottom is the fastest. Remember that it's coming down though. On the bottom is the fastest, and then as you go up, so basically as the ball comes down, it becomes faster and faster. So how do we use this to compare the times taken to traverse up and down? Okay, so do you agree that I hope you agree that the time taken to traverse from this x equals to 0 height to the x equals to h height is equals to this distance, 0.1h, divided by the average velocity here, plus another 0.1h divided by the average velocity here, plus another 0.1h divided by the average velocity here, and so on. So basically what I'm doing here is I'm splitting the entire journey up as into many small distances, and to calculate the time the ball takes to traverse each of the small distances, I take the small distance divided by the velocity at that point. So expressed in integral, it can be written as the time taken to traverse t1, the entire journey, is equals to the integral from 0 to height h of a small distance divided by the velocity at that distance. So yes, yeah. So what is important to compare here is that what is the important comparison here is that v2 as a function of height is always smaller than v1. And why is that so? This is because let's start off from the top, okay? So we start comparing the top. We know that at height h both of them are 0. Okay, at height h both of them are 0. So at height h both v1 and v2 are 0. However, remember that when you went from 0.9 to height h, when you went from 0.9 h to height h, you the velocity decreased, the speed decreased from here to here was caused by both gravity and air drag, meaning that the jump from here to here is sort of combination of both of these. Whereas when you went from this one, when you went from h to 0.9 as it's falling down, the speed increased, but it was only increased by gravity minus the air drag. This means that, logically speaking, if let's say I have a ball that is currently at 0.9 h, right, is moving up at let's say 1 meter per second, then gravity and air resistance acts to decrease that 1 meter per second to 0 meters per second. And you require both gravity and air drag to work hand in hand together to decrease the velocity by 1 meter per second. However, when you have the ball falling from here down to here, then the gravity, the air drag is acting against gravity, meaning that you have gravity minus air drag that increases the speed from 0 to, let's say, half a meter per second. So what I'm trying to say here is that if we just look at the situation where if we just look at the heights from 0.9 h to h, right? Let's say initially it's going upwards at 0.9 h, is going up at 1 meter per second, and then it requires both gravity and air drag to bring it down to 0. So it brings it down by 1 meter per second. And then from here, because you don't have gravity and air drag working together anymore, in the scenario that you had gravity and air drag both acting downwards, then sure, by all means, v2 at 0.9 h is also going to be 1 meters per second, because it's symmetric, right? To go up and then to come down. But because in this case gravity and air drag do not work together, we can assert that v2 at 0.9 h is definitely less than v1 at 0.9 h. And going from 0.8 h to 0.9 h, a similar procedure ensues. So we have v2 at 0.8 h is going to be less than v1 at 0.8 h, and so on for all the way down, meaning that if we take two videos, right, one of the ball going up and one of the ball going down, then if we measure the velocity at each height level, we measure the velocity for both the cases of going up and going down, or rather we measure the speed of the ball when it's one time when it's going up and one time when it's going down, then we are going to get that the speed on the way down is always at any particular height, the speed of the ball going down is going to be less than the speed of the ball going up, by this reasoning over here. So in the end, because we have divided up the entire journey up and down via the same small distances, we can then conclude that because v2 is slower than v1, v2 is less than v1, hence the time taken is the reciprocal, right? Because the faster you travel, the less time you take, and hence the time taken to travel up is less than the time taken down to travel down. So to recap my entire argument, sorry it's been quite a long video. My argument is that if we plot the velocity as a function of height rather than as a function of time, then on the way up and on the way down, at every single height level, at any height level we choose, the speed going up is going to be more than the speed coming down, because on the way up you had gravity and air drag working against the speed, and on the way down you had gravity and air drag working against one another, and they both sort of end at the same VH equals to 0. So I hope this clarifies the doubt a bit more. I've finally found a more rigorous explanation. Yeah. So hope you enjoyed the video. Yeah. Bye.